I really love the Fundamental Theorem of Calculus. I think it's just such an amazing theorem because it tells me what to do with this object right here. I read this as the integral from a to b of f of x dx. This is what we call a definite integral. And this is very often a number. And the fundamental theorem says that if f is continuous on an interval from a to b, so I need f is continuous on that interval, and I need to know that capital F is an antiderivative for lowercase f on a, b. And I need this on AB because like capital F might be an antiderivative in some places and not others because of piecewise defined functions and stuff like that. Just kind of technicalities. The main point of it is what do I do in order to come up with the number or the expression that the definite integral is? I take my antiderivative and I evaluate it at B, and I subtract the antiderivative evaluated at A. So this is the thing that couples together antiderivatives and evaluation of functions. And I think this is so super cool that it works like this. This theorem suggests a two-step process for me when I'm doing a definite integral. I feel like the step one process is we need to find capital F in order to be able to answer this question because I'm going to evaluate it. And then I'm going to, as step two, evaluate capital F at B and capital F at A. And then three, I'm going to subtract those values. And very often I would merge step two with step three. And so I want to really evaluate those two things. Okay. The evaluation part tends to be the easier part, and finding antiderivatives in general is a difficult problem. In the training problems that we're going to keep giving you, the antidifferentiation is, while tricky in places, not impossible. And there are functions for which no antiderivative with closed form exists, which I think is just like, that's just another super cool fact in the world of calculus. Like, what? There are functions where I don't have an like, what? What are you talking about? I think that's so super awesome. I want to do a little bit more notation for you before I step away and do an example problem and then call it good for this video. So as an example, as notation, I want to also write the integral from a to b of f of x dx is equal to capital F of x vertical bar a b. So let me narrate this. This is the integral from a to b of f of x dx is equal to capital F of x evaluated from a to b. And I really like to put x equals on both of those to indicate what I'm supposed to do with a and b. Like, where do they go? Oh, they replace the x in the argument, and there's an implied difference going on here as well. So this is equal to capital F at b minus capital F at a. Let's do a definite integral using the fundamental theorem of calculus, shall we? Let's integrate from 0 to, let's go to 5 pi over 4 of, let's use a trig function. Let's go with, how about let's go with cosine of x dx. So step one, and this is I've got to anti-differentiate my integrand. This part in here is what we call lowercase f of x as a generic name for it. Maybe it has another name that's not lowercase f, and that's fine too. It doesn't have to be f. So we've got to anti-differentiate this. So if I do that, then capital F of x is equal to, let's see here, what do I take the derivative of to get cosine? I take the derivative of sine to get cosine, which means that the integral from 0 to 5 pi over 4 cosine of x dx is equal to sine of x evaluated from 0 to 5 pi over 4, where I have x's right there. So what am I going to do? I'm going to take and evaluate at 5 pi over 4, and I'm going to subtract evaluation at 0. This is equal to sine of 5 pi over 4 minus sine of 0, right? So the lower one goes on the right, the upper one goes on the left with a minus sign between them. And I know that sine of 0 is 0. And I just have to remember what 5 pi over 4 is for sine. Let's do a quick little unit circle on this one right here. So, boop. If I go around my circle, this is where I'm at 4 pi over 4, or pi. And then 5 pi over 4 is if I go down here. And I know that that sine is the y-coordinate. I know that it goes cosine, comma, sine as points on this, and it's negative. We're focusing on sine. We're below the x-axis, so it's going to be negative. And I remember that it's one of these 45-degree ones, which means that this is minus root 2 over 2. If that was a little bit mysterious to you, I would encourage you to review your unit circle and keep that handy. The unit circle is just such a delightful thing to have. Yeah, so I did step 1, and then I did, so step 1 was anti-differentiate, and then step 2 was evaluate. In this particular case, the anti-differentiation was actually easier than the evaluation, but that is generally not the case. So that's the fundamental theorem of calculus. It tells us how to do a definite integral as the difference of the antiderivative evaluated at the upper and lower endpoints of the interval. Thank you so much, and I wish you all the best as you practice your integration.